Okay, good morning, everyone. So this lecture is about an introduction to time series. It doesn't pretend to be, to explain everything, but at least gives a summary of the main things, the most important things in time series. So the outline of the presentation, I'll try to introduce time series. I'll talk about methods for analysis, classification, analysis steps, models, linear regression, especially, and I'll give with three examples. And then I will also upload the videos which detail how this has been coded. So first of all, as an introduction, I would say that time series, in fact, are series of data points indexed or listed in or ordered in graphs in time order. A time series is usually a sequence taken at successive equally spaced points in time. It is a sequence of discrete time data. So examples of time series are heights of ocean tides, for instance, counts of sunspots, and the daily closing value of the Dow Jones Industrial Average. A time series is very frequently plotted via a run chart, which is a temporal line chart. Time series analysis. Time series analysis gathers all methods used to extract meaningful statistics and other characteristics of the data. Time series forecasting is the use of a model to predict future values based on previously observed values. Time series data have a natural temporal ordering usually, and this makes time series analysis distant from cross-sectional studies in which there is no natural ordering of the observations. For instance, explaining people's wages by reference to their respective education levels, or where the individual's data could be entered in any order. And we've seen previously in this course such examples. Applications of time series models will often make use of natural one-way ordering of time, so that values for a given period will be expressed as deriving in some way from past values rather than from future values. Time series analysis can be applied to real value, continuous data, discrete numeric data, or discrete symbolic data. Time series are usually used in statistics, signal processing, pattern recognition, econometrics, mathematical finance, weather forecasting, earthquake prediction, control engineering, astronomy, communications engineering, and largely in any domain of applied science and engineering which involves temporal measurements. Classifications of time series. Methods for time series analysis may be divided into two main classes. There are frequency domain methods and time domain methods. Frequency domain methods include, for instance, Fourier transforms, while time domain methods include linear and nonlinear regressions and smoothing methods. Methods for time series analysis may be also divided into linear and nonlinear and univariate or multivariate methods. Or you can also divide time series analysis techniques into parametric and non-parametric methods. While the parametric approach assumes that the underlying stationary stochastic process has a certain structure, which can be described using a small number of parameters, for example, using an autoregressive or moving average model. Now I'll try to go through the analysis steps for time series. First of all, about the motivation of doing the work. The primary goal of time series analysis could be forecasting, like in econometrics, quantitative finance, signal detection, like in communication, or clustering and classification, like in data mining, pattern recognition, or machine learning. In the context of signal processing, for instance, control engineering and communication engineering, it is used for signal detection. Other applications are in data mining, pattern recognition, and machine learning. Exploratory analysis, which is the second step, which is a straightforward way to examine a regular time series, are simple as for using, for example, simple line charts. Other techniques may be used and include used to separate into components representing trends, seasonality, slow and fast variation, like we call levels, cyclic irregularity, and spectral analysis to examine cyclic behavior not related to seasonality. Curve fitting, it's the process of constructing a curve or mathematical function that has the best fit to a series of data points, possibly subject to constraints. This could involve either interpolation, where an exact fit to the data is required, or smoothing, in which a smooth function is constructed that approximately fits the data. A related topic is regression analysis, which focuses more on questions of statistical inference, such as how much uncertainty is present in a curve that is fit to data observed with random errors. Now I'll talk about the main models we have for time series analysis. Models for time series data can have many forms and represent different stochastic processes. When modeling variations in the level of a process, three broad classes of practical imports are the autoregressive, which we may note by AR models, the integrated, which we note by the I models, and the moving average, which we may note by the MA models. These three classes depend linearly on previous data points. Combinations of the ideas produce autoregressive moving average, like the ARMA, and the autoregressive integrated moving average, like the ARIMA models. Empirical investigations can indicate the advantage of using predictions divided from nonlinear models also over those from linear models, as for example, in nonlinear autoregressive exogenous models. Among other types of nonlinear time series models, there are models to represent the changes of variance over time, what we may call heteroscedasticity. These models represent autoregressive conditionals, heteroscedasticity, ARCH, and the collection comprises a wide variety of representation like GARCH, TARCH, EGARCH, TriGARCH, CG-GARCH. Now I will talk briefly about the notation we mainly use in time series. A common notation for time series is to use the X variable for the input, like x1t, x2t till xnt, to represent the different n inputs features, which with respect to the time t. A common notation for time series is to use, for the time series output here, is to use y1, y2 till ym to represent the different m outputs with respect to the time t. The whole purpose is to look for approximation function, fj, of the input that could approximate the output for j going from 1 to m. Here, in general, you may consider that you may have different outputs to try to forecast or to predict. So y hat j of t is in fact an approximation value or an approximated value of yjt, okay, which uses the approximation function fj. A good approximation would try to minimize, of course, the approximation or the estimation error, which is measured by the absolute value of the difference between yjt and y hat jt. One way to do that is to minimize what we call the root mean square error, RMSE, which is the square root of the sum of the squares of the errors. Now we'll talk about the linear regression model. The linear regression model assumes that there is a linear relation between the output and the inputs. So y hat of t is in fact a linear combination of a1 x1t plus a2 x2t plus till xnt plus some what we call a constant or a bias for all t going from 1 to the time horizon, which is capital T here. Well, the coefficients a1, a2, an, and b are obtained by solving in fact, the RMSE minimization problem, the root mean square error minimization problem. And this could be easily converted to the following problem, where we substituted y hat by its linear approximation. So the minimization of the sum from t equals 1 till capital T of yt minus a1 x1, a2 x2 till xn till an xn here, which is missing. I'll add it here. Okay. And plus the bias b, all squared. So to make sure that we give more importance to larger errors and less importance to small to tiny errors. And this usually works quite well. So linear algebra here plays a big role by rewriting the model as y hat equals ax plus b here. So what did we do here? We introduced the vector y capital T, which gathers all the input or the output variables in one vector. And A is the matrix which contains or the vector that contains all the coefficients a1 till an. And X here is a matrix with dimensions t by n, with elements xit, while I goes from 1 to n. So this matrix, in fact, summarizes the whole input. Okay. So, and finally, B is the bias vector, which is just the one column of ones multiplied by the constant B. So, the solution to this problem, if we introduce here, let me just erase this, let it be here. Okay, that's fine. So the solution to this problem, when you write y hat equals ax plus b, now could be rewritten as c, which is using c, which is containing a, b, and z, which is containing the vector x, the matrix x and 1. The whole model rewrites as y hat equals cz. And one could notice here that z is t by n plus 1, and generally not a square matrix. So the idea here is to use the pseudo-inverse matrix to solve the problem. So we introduce the pseudo-inverse matrix Z plus, and the observed output y yields that C would be equal to Z plus times y. Okay, so now that we obtained Z plus, which we recall is either equal to ZT times Z inverse times ZT, or the other way to do it from the right side is to say that it's ZT times ZZT inverse. The beauty of this solution lies in the fact that C is the least square error solution to the problem, and the RMSE problem is solved by simple pseudo inversion here. Okay. Let me just erase this. Okay. So now we start by talking about the examples we will detail. I will detail in the next videos and implementations. So the simple case here in the file which we will use, which is called linear regression pseudo inverse, we encoded two data vectors x1 and x2 with 28 entries each, and we also generated a vector of outputs y such that y is equal to 2x1 plus 4x2 squared plus 5. And you see this is a nonlinear relation, all right. And we defined here z to be to contain x1, x2, and 1 vectors, and computed z plus using the p inverse function, the pseudo inverse function. And we computed the least square solution, c plus, which is z plus times y, and obtained the predicted vector y hat, which is c plus times z. The RMSE obtained is equal to 0.2419, and displayed 2 plus to compare y hat to y. And even though we use the linear regression to predict an already known nonlinear relation, the two curves, in fact, fit quite well. Okay. The second case, which we will detail, is about random data. So in the file, what we'll talk about random linear regression, we randomly generated 4 data vectors, x1, x2, x3, and 4, and with 50 entries each. And we also generated a vector of outputs y such that yt is equal to 2x1 plus 4x2 squared plus 10x3 plus 6 over 1 plus x4 plus 5. We also defined z, which is x1, x2, x3, x4, 1, and computed z plus using, again, the pseudo-inverse function. And we computed the least square solution c plus, which is z plus times y, and obtained the predicted vector, which is y hat equals c plus times z. We obtained a root mean square error, which is about 0.02785, and displayed 2 plots, which in fact 2 curves, 2 plots which curves really quite well. And the final example we are giving, which is more elaborative, where we try to import the data correctly from the data file. So in the data file linear regression, we did the travel times data file from an old project. And so the main goal here is to estimate the travel times between points. And the CSV format here is used, but other formats also could be used. The Panda library in Python is used to read from the CSV file. And we noticed that here df in the Python implementation is just a data frame and needs to be refined to extract that data. And at the end of the day, we obtained a quite good prediction with the pseudo inverse method, but this might be subject to improvement. So I'll stop here. So we'll move to the next part, which details the implementation on these tiny examples. Thank you very much.